Alright, gang. This would be our AP2 circuits basics that I want to talk about. So this is that recorded information that I want you to know. Potential difference. Potential difference, something we just got done talking about. Potential difference, another name for it, is voltage, which is also known as your EMF. So in a battery, a series of chemical reactions occurs in which electrons are transferred from one terminal to another. This is a redox reaction, by the way, in your chemistry class. There is a potential difference then between these poles because of the transfer of those electrons from one terminal to another. The maximum potential difference a power source can have is called its electromotive force, which is why we also call this its EMF. The term isn't actually force, simply the amount of energy per charge. So if you remember, it can be just V, it can be a delta V, or it can be our lowercase epsilon. That's what that letter is for EMF. So just so you know, again, this is all what batteries have. Batteries have potential difference. They have voltage, which is also known as the EMF. For a basic circuit, all circuits are going to have three parts. They're going to have a source of energy, they're going to have a closed path, and they're going to have a device which uses the energy, which is typically called a resistor and or a load. If any part of the circuit is open, the device will not work. So if your energy source, which is typically your voltage of your battery, if it is out of juice, then it doesn't work. If your path is not closed all the way, then it won't work. If your device here, which we show as a light bulb, is broken, then that pathway is going to be open, so it won't work. So any one of the three, if it's open, it won't work. Electricity can be symbolic of fluids. We can kind of talk about it the same way. Circuits are very similar to how water would flow through a pipe. And really, in circuits, we're talking about that electron movement. So electron movement would be like the water primarily. A pump basically works on two important principles concerning the flow of water. There's a pressure difference from one end to the other, where the flow begins and where it ends, and a certain amount of flow passes each second. Well, a circuit basically works the same way. There's a potential difference or a voltage difference where the charge begins and where it ends. And the amount of charge that flows per second is called the current. So when water has a current, kind of that's the same as our electrical current. So it's the amount of charge per second instead. So that's kind of a way of thinking about electricity through a circuit. Now, current is defined as the rate at which charge flows through a surface. One of the formulas on your formula chart is I equals Q over T, where Q is our coulombs, and Q is our coulombs, and C is our unit, and T is in seconds. So coulombs per second is actually an ampere, which is sometimes shortened to an amp, which we shorten to just the letter A. But you do need to know how all these units work and how they're developed. So amps is a derived unit from coulombs per second. So the current is in the same direction as the flow of a positive charge for this course. And what that means is that the positive is going to go away from the positive terminal and into the negative terminal of a battery. So that's how we always look about how the current is going to flow as well. So the I stands for the intensity of the current, and so that is that current value. There are two types of current. There's a direct current, which means that it just flows in one direction, and that's typically what we talk about with a battery, that it goes out of the positive and into the negative. So there's a direct current flow as it goes in. But then there's also an alternating current, okay? And the alternating current reverses directions many times per second. This is what happens when you have something plugged into the wall. So it suggests that AC devices turn off and on and off and on and off and on. So that's why the prong of your outlet is so important, because really the electricity comes in one way and then it also comes in the other. So it alternates as time goes by. Ohm's law. We talked about Ohm's law last year in your physics classes. The voltage or the potential difference is directly related to the current when the resistance is constant. So you can say that voltage is proportional to, is directly proportional to your current. If you're going to say that, though, your R has to stay constant. And your R value is your resistance value. Now, the formula on the formula chart is your V equals IR, or that lowercase epsilon equals IR. Since R equals the change in your voltage divided by your current, then the resistance is actually the slope of a voltage versus current graph. So you do need to make sure that if you're given these types of graphs, you understand that really you're taking the voltage and dividing it by the current, which is the formula for resistance when you're using Ohm's law. So just make sure you understand how they all connect and how you can always look at slopes and areas under lines to find different information on graphs. Now resistance, so since we've said this word a couple of times now, resistance really is defined as the restriction of electron flow. It's due to an interaction that occurs at the atomic scale. So for example, as electrons move through a conductor, they're attracted to the protons actually of the nucleus of that conductor itself. This attraction doesn't stop the electrons, but it slows them down for a bit and causes the system to waste energy because it goes, whoa, hold on, do I want to stay here or do I want to keep going? And typically those electrons are going to be pushed to keep going, but they do at least slow down. So that causes some energy loss. So the unit for resistance is an ohm, which is that upside down omega sign. That's the capital omega sign for the Greek symbols. Now electric power, we've already learned that power is the rate at which work or energy is really done. It's a rate. So really it's just work divided by time. So circuits that are a prime example of this, as batteries only last for a certain amount of time, and we get charged an energy bill each month based on the amount of energy we use over the course of a month. All of those things are also known as power. So it's interesting to see how certain electrical variables can be used to get power, though, and there's lots of different ways to do it. If we just take voltage and current, for example, voltage is joules over coulombs, and current is coulombs per second. So if you take voltage times current, and you take those units and you combine them, you end up with joules and coulombs on top, and coulombs and seconds on the bottom. When you have coulombs on top and bottom, it cancels out. Well, joules per second is a watt. Well, watts is the unit for power. So there's lots of different ways to kind of get these units to occur, but that's one way of looking at how those units would work together to create the watt, which is a power unit. So that's how that first formula works, is power is voltage times current. You could also then look at it as, well, if we have V is equal to IR, well, we could substitute that V in to our power formula, and so we would have IR times I. Well, I times I is I squared. So another way to look at the formula would be I squared times R. And then we could also look at it as, well, what is I? Well, I is V over R when we're using Ohm's law. So if we took that formula and substituted it back in, and let me go ahead and do that. So if I take this formula and substitute it in up here, then I now have V times V over VR, which if I do V times V, that's V squared divided by R. So these formulas can be used too. They're simple derivations of the power formula, but they're different laws or different versions of Ohm's law being substituted in. So it's important to notice how Ohm's law and the power formula can be related, because you may not always be given all the information that you're going to need, but you can substitute a different formula or look at it in a different way and still solve for the information. That's really all I wanted to go over today. We will go over the basics of what types of circuits there are in a different recording, but we'll be done for now. Thanks, guys.